So thanks so much for coming to my presentation. So I did this project with Dr. Ailsa Keating on the faithfulness of the canonical representations of a class of generalized Coxeter groups. So I'm going to start by defining what a Coxeter group is. So it's group W that's generated by S1 up to Sn subject to relations of the form SI/Sj to the Mij is 1. And the conditions on Mijs are that Mii have to be 1 for all I, which means that each of the SIs need to be involution, i.e. they have order 2. And the Mijs can be natural numbers or they can be infinity, where an infinite order between Si and Sj just means that there is no relation between Si and Sj. And the Mijs are stored in the Coxeter matrix M, which is symmetric with ones in the diagonal. And it's symmetric because Si/Sj inverse is just Sj/Si because these are all involutions. It'll be helpful to introduce a diagram for all of this now. So I will do that by using an example. So for this group that I've written down, this will correspond to the matrix, Coxeter matrix M that I've written down, where the 3 here is the 3 here, the 6 here, the 6 here, and the 2 is the 2 here. But it's more convenient to view this as a diagram, a Coxeter diagram, which is a label graph where the vertices are the generators. So we got S, T, and U. And then you put an edge between the generators if and only if they don't commute. So here U and S commute because US squared is 1. So I don't put an edge there. But S and T don't commute, so I put an edge, and T and U don't commute, so I put an edge there. And I put the order of their product on as a label on the edge. So therefore ST would be 3 and T would be 6. And because the 3 is the smallest number I can put as a label, we often just drop the 3 when it's there. And obviously you can flatten this graph into the line thing, that I've already written down. A very important example of a Coxeter group is the dihedral groups. So if you recall that the mth dihedral group D2M is the set of isometries of a regular 2M gon, it's usually written in this way, and you can check that this is the same as if I write this down. And clearly, currently, this is not yet manifestly a Coxeter group because one of the generators R has order M, which is not 2 in general. But if we write T to be SR, then what we find is that these relations then become this on the bottom. And therefore, this is now Coxeter because the generators S and T are involutions and ST has order M. And the Coxeter diagram is this thing. Now, the reason this is important is because the dihedral groups are kind of the most basic kind of non-trivial Coxeter groups because they have 2 generators. And you can see that they're generated by 2 reflections, which have reflection axes that meet an angle pi over m, because T just turns out to be this reflection here. And the product of them has order m, which will be very important for later on. But briefly, I'll digress to a more general problem called the word problem, which is for any group that is defined as kind of generated by a set S subject to some relations R. That's not necessarily the Coxeter kind of relations. For any little w in capital W, we can write it as T1 up to Tk for some Ti and S because W is generated by S. And the K-tuple T1 up to Tk is known as a word for W. And the word problem is simply, given such a kind of product, how can we figure out whether this product is actually just secretly the identity element? For a general W, the word problem is hard and not necessarily solvable. So there is no algorithm that's guaranteed to solve in finite time. However, for Coxeter groups, there is a nice combinatorial solution because the forms of the relations right up in the definition here are just kind of nice. So there is a nice combinatorial solution. So for instance, for this group here that I've written down, if I wanted to check whether this element was just the identity element, I'm guaranteed to be able to reduce this down to 1 if it is actually just 1 via substitutions of the form TST going to STS or so UTU going to TUT, and just replacing SS to be 1, TT and UU to be 1, etc. And obviously, if like in this case, ST at power 3, and that's why I'm doing the substitution, and if instead ST at power 4, then I'd be making the substitutions STST going to TSTS and friends. But the point is that the substitutions just have to be of the same length. Well, you don't have to increase the word length in order to get from an element down to 1, if it is indeed the identity element, which of course means the word problem is solvable because you start with a word of finite length, it will take you definitely finitely many substitutions to get down to 1 if you don't have to increase the word length. So that's kind of nice, but it would be even nicer if we could find a faithful representation for these groups. So once again, let W be Coxeter, and we want to find a representation which, for the purposes of this project, is just a homomorphism phi from W to GLNR, where n is the number of generators of W. If we can find a faithful representation, then this would really easily solve the word problem, because to check whether such a word T1 up to Tk is 1, all I have to do is compute the product of the matrices that phi sends T1 up to Tk to. And multiplying matrices is a lot easier for a computer anyway than making lots of random substitutions. There are also other reasons that we're interested in faithful representations for Coxeter groups, but these are geometric and I don't understand them. Now note that in order for such a representation to be well defined, we need phi to respect the relations here. And that means that the images of the SI need to obey the same relations that were used to define W. Now, I'm going to do a construction here that allows us to find such a representation. For B a bilinear form, I'm going to define rho I to be the ith generalized reflection given by this formula here. And this is known as the generalized reflection because in particular, if we just replace this with the standard inner product, then this is of course just the standard reflection in Rn about the ith standard basis vector. So just replacing the standard bilinear form with another kind of bilinear form, it makes sense to call it a generalized reflection. And indeed, they enjoy kind of properties such as these rho i's are involutions, i.e. rho I squared is 1 for all I. And the idea is if we let phi be a homomorphism that sends Si to rho I for all I, we want that this is true. And this is indeed true if we choose the following bilinear form. Now, if M is the Coxeter matrix for W, then we let the cosine matrix B have ij entry minus cos pi over mij. And we observe that with respect to this bilinear form, EI and EJ meet at this angle. And the reason this is a nice angle is we recall that D2M was generated by reflections that have reflection axes meeting at pi over M, and that their product has order M, which is exactly what we want. We want that the order of pi I, rho I, rho j to be Mij. This is not exactly a proof, but you can take my word for it that this is indeed true. And therefore phi is well defined, and we can call it the canonical representation for W. So that's saying that phi is well defined. The fact that phi is faithful is true, but much harder, and is due to a theorem by French mathematician Jacques Tietz. Once again, I'm not going to try and explain it here. So let's do an example. For this Coxeter group, which has generated by 3 generators, whose pairwise product is all 3, as you can see by all these unlabeled edges. So this is the Coxeter matrix, and the cosine matrix, recall, has this ij entry. And minus cos pi over 3 is minus a half, hence all the minus a halves there, and minus cos pi is 1. So all the i's, all the diagonals on the B are 1. And recall this was the formula for rho I, and this will be the same as the matrix I minus 2b E11, where E11 is this elementary matrix, which computes to this thing. And similarly, rho 2 and rho 3 compute to these. And you can check once again that rho I, rho j to the Mij is 1 for all ij. So this is well defined and is faithful once again by that theorem by Tietz. Now, all this has been kind of in literature so far, and we've not really done anything new yet, but here we introduce a new kind of construction that generalizes the notion of Coxeter groups. So we recall that we've been able to define Coxeter groups using the Coxeter diagrams. And from this point onwards, I'm not going to care about any labeled edges anymore. All the edges will be unlabeled, and therefore, if, say, S and T have an edge between them, that will mean that ST cubed is 1. And notice here that for this group, I've shaded in this triangle, and this shading represents the relation STUS is TUST. And this is a fairly weird kind of relation. And once again, there are geometric reasons that back up the fact that shading should correspond to this. But it also turns out that this group is isomorphic to this Coxeter group here that's generated by UT and STS. And we can ask the same question of whether or not there is a non-trivial representation phi from W to GL3R. And recall that for the unshaded triangle above, we took the bilinear form with just kind of lots of minus halves everywhere apart from the diagonal. It turns out that if we pick one of these pairs of minus halves and make the sign plus and play the same game with generalized reflections, we do indeed get that the rho I, rho j's once again satisfy the right kind of orders. And in addition, they satisfy the weird relation that we wanted above. And therefore, this is a well-defined representation, and I'm going to call it a canonical representation for W. Now, the kind of plus a half seem to have come out of nowhere. I'm going to give a bit of a motivation for this. If effectively, all these plus a halves come from isomorphisms between these shaded triangles and the flat kind of Coxeter group that I mentioned before. And in particular, you notice that I'm picking one pair to be plus a half at a time. And so this will correspond to a certain edge being special. So in this case, it's the ST edge that's special. In this case, it's the SU edge that's special, corresponding to this pair. And here is the TU edge that's special, corresponding to this plus a half pair. And each of these different bilinear forms you can get by considering a different isomorphism from this shaded triangle to this flat kind of Coxeter group by choosing different generators. So let's do a kind of bit more kind of a complicated example where we have this generalized Coxeter group here that now has 4 generators and has one shaded triangle and no, the other one is not shaded. So once again, we have this weird relation between ST and U, but we don't have that for TU and V because there is no shaded triangle between UT, U, and V. When choosing our bilinear forms, we need to make sure that each shaded triangle has one red special edge and each non-shaded triangle doesn't have any special edges. So we can pick ST to be a special edge and therefore get this bilinear form. Or we can pick SU to be this special edge and get this bilinear form. Picking TU would be bad because this would then mean that TUV has a special edge and is therefore considered shaded by the bilinear form, which is not good. And obviously, like all the other kind of the terms are either minus a half or 0, depending on whether they have an edge between them, which agrees with the previous notion of the Coxeter matrix and the cosine matrix. A little warning here, different choices of the red special edges will give different canonical representations, and it's not necessarily true that these properties are shared by these different canonical representations, for example, faithfulness, which is important for our next kind of question, which is then, are these canonical representations faithful? Now, if W is actually isomorphic to a Coxeter group, then any canonical representation for W will be faithful because the representation came from some sort of isomorphism from that Coxeter group. Otherwise, there is no known theorem that classifies when the canonical representation is faithful. And to be honest, I'd be fairly surprised if there was one, I think, because the one that was done by Jacques Tietz for Coxeter groups was fairly complicated, and we already noted that Coxeter groups are special and nice in their relations. So what I did for a lot of my projects was check manually using MATLAB whether these representations were faithful. So that in particular just means checking whether there are different elements W1 and W2, such that the phi of W1 is phi of W2. Which of course is the same as checking if there's a non-trivial element that gets sent to 1. Now, if W is infinite, then of course we can't show that phi is faithful because you can't check all the elements of W. But you can show it isn't faithful if you can come up with such an example of W1 and W2. But let's back up a bit, because in order to find a non-trivial element W, such that phi of W is 1, it's necessary to deduce whether it is actually non-trivial, which is solving the word problem. And we recall that for Coxeter groups, the word problem was fairly nice to solve because you just had to make substitutions of the same length. But for generalized Coxeter groups, this is not true. Sometimes you do need to make substitutions that increase the word length, such as from STU to TU STS, which means that certainly I haven't been able to solve the word problem yet, which is annoying, but sometimes there is a non-combinatorial way to prove that something is not trivial, which I will come to in a moment. So for the project, I investigated a few groups that were and their canonical representations. So it turns out that this sequence of 1 to 6 shaded triangles, these are all actually isomorphic to Coxeter groups, and therefore their canonical representations are faithful. But when you go up to 7 shaded triangles, this is no longer Coxeter. And for this choice of special edges, I ran my MATLAB program on the canonical representation up to words of length 30, and I couldn't find any non-trivial element that was sent to 1. Once again, this doesn't mean that it is faithful. It just means that I can't show it's not faithful. But according to Dr. Keating, there are geometric reasons that suggest that faithfulness is likely, although once again, I do not understand these reasons. Another group that I studied was this kind of corner shape kind of piece, which is again not Coxeter. But again, my program showed that up to, if it's correct, it shows that there are no non-trivial elements up to length 26 that get sent to 1. So once again, it may well be faithful. And again, there are geometric reasons that I don't understand that suggest that faithfulness is likely. So you might ask that, could it actually be that all of these representations are just faithful? And the answer to this question is no. So if you look at, if we consider this group here, my MATLAB program did actually find an element that wasn't trivial, but was sent to the identity element. And therefore, what this would imply that phi is not faithful. But of course, we have to check that this element is not actually the identity element in secret. And there was a really nice way to check this that Dr. Keating suggested, which is if you fill in this extra triangle, you make a new group, which I call W prime with canonical representation phi prime. It turns out that in this new generalized Coxeter group, phi prime of S1 up to Sk is not 1. And of course, that must mean that S1 up to Sk is not 1. And if it isn't 1 under these relations R prime, which contains my original relations R, then certainly it can't be 1 when I have fewer relations in R. And this is a way to show that this W was actually not the identity element, and therefore phi was not faithful. I then considered these extra groups, which just consist of, because for this group, it was 2 kind of unshaded triangles sandwiching the shaded triangles. So I thought maybe I should add more shaded triangles between the unshaded triangles and see what happens. And similarly, with these choices of special edges, it turns out that there is also a non-trivial element that's sent to the identity matrix under these canonical representations. So once again, these are not faithful. And once again, I checked that they weren't the identity using a similar method by filling in this extra triangle and doing a similar thing to the above. So once again, I went from 2 unshaded triangles sandwiching 1, 2, and 3 shaded triangles and found that the canonical representations were not faithful. Naturally, this led me to conjecture that however many kind of shaded triangles I can sandwich between the 2 unshaded triangles, the canonical representations indicated by, well, with these special edges is not going to be faithful. And it turns out this is actually true. And I have been able to exhibit an explicit non-trivial element in each group that's mapped to 1 by the canonical representation. I've case checked this using MATLAB to be true and up to 99, but I have also been able to prove it theoretically, although I haven't written it up properly yet. So to kind of like closing remarks for this kind of theorem, I guess, is that, well, while this doesn't once again mean that other choices of special edges can't yield a faithful canonical representation, because there is no theory to suggest that choosing different special edges will give me kind of representations of the same kind of property. But nonetheless, it is kind of still quite nice that there is an infinite set of these generalized Coxeter groups that have a canonical representation that is not faithful. And once again, I don't know whether this is actually useful for maths, and certainly a lot of this is important for kind of geometric reasons that once again are over my head. But I enjoy doing this project, and yeah, thanks so much for listening, and special thanks, of course, to Dr. Keating for not only supervising me in the project and replying to loads of my emails, but also funding it with some of her grant money. Yeah, so thanks very much, and that's the end of my presentation, and I'm happy to take any and all questions.